Hi, today we're going to continue talking about EDTA. This is going to be a bit of review, so hopefully that'll speed things up dramatically because we've kind of already talked about this before, even though this is when your book finally gets to it. Fractional composition. So just to put a little bit more information onto EDTA and how it works, here's another way to draw the structure. It is designated with a Y to represent the rest of the molecule, everything that isn't an acidic hydrogen atom. But the six forms, the six ionizable hydrogens are shown, highlighted here. And then there are the corresponding pK values. As you can see, the first four values correspond to the outer carboxyl groups, and the fifth and the sixth refer to the ammonium groups. All of them do get lost. So this subject, this molecule, this particle, as we have it shown here, we would call that H6Y2+, as in the two ammoniums are giving it two positive charges, the four acids are electrically neutral. As you lose protons, we would then work our way to H5Y+, H4Y, as you can say, as it says here, the neutral acid, which would work then all the way down to Y4- to show the fully deprotonated form. Yeah, I can't quite remember what point I was trying to make on this other than just showing a little bit more information. Now, what's interesting is you see the word letters EDTA when you look on food labels, and I think people are rightfully wanting to understand the food that they eat. If there is an EDTA in the food they eat, or if it's in their homes in any way. The problem is, you go looking online and you see things like this. Now, what I really like about teaching this lesson is I like showing this image and saying, okay, this is impossible. I found it on the internet, and if I don't make a point of pointing it out to you, when we get to the project at the end of this unit, you're going to include this image, and you need to be able to evaluate it. This structure is inconsistent with what I just showed you. So I'm going to give you like 30 seconds. I'm going to count in my head. I want you to try and figure out why this is an impossible structure. What is wrong with it that's actually causing this to be impossible? I just realized you could pause it if you needed 30 seconds. So I'm going to start talking. First, given what is highlighted, I would call this species H4Y. This is our neutral species. You can see no charges being shown. However, if we go back to what we showed here, H4Y would be losing these two hydrogens. So what we should have is two acids and two ammoniums. We see four acids. Technically, in terms of increasing the pH and changing the predominant form of the chemical structure shown, you're going to lose the acid H's before you lose the ammonium H's, which means this and this. Now, we're not going to split hairs over which acid gets lost at which point, so I'm just going to kind of pick them at random. You can see that the four of them are lost within 3 pH units of each other, so it's not super important which one happens which, because also they're all going to be in equilibrium with each other. But these two ammonia, nitrogens, should have hydrogens bonded to them, and the two acetate group should be negative. This structure is chemically consistent with what we understand about how these particles work. There's something to be said for taking the time to go through the internet and vet what you're looking at to make sure it's actually chemically relevant, because I've just seen these submitted so many times, and it breaks my heart to see it. To bring in something that we've talked about before, this graph shows the fractional composition of EDTA as a function of pH. And it's a lot. Now, as you can see, given our original values, that 3 of them are below 3, and the next one is at 6, and the next one is at 10, what we can see is there is some significant separation between pK5 and pK6, so that this hy3 minus, the y4 minus, and the h2y2 minus, those all have significant separation. So if we were to look at a pH-based titration curve, there'd be nice separation and clear endpoints, equivalence points. What we see over here, though, is that these 4 different forms that are all stacked down by 3, you can see that none of them reaches a high fractional composition or high enough to be clear. So if we were to look at a titration curve for this, I'd probably only see 3 peaks, maybe 2, maybe 4. It'd be very messy. But that's not entirely what we're going to talk about today. Oh, maybe it is. No, we're not going to look at a titration graph. I can guarantee you that. What I can say is that the functionality of this structure and the binding that we've seen before are all a factor of these binding sites being electron rich, deprotonated. So there's a huge emphasis on understanding how much of your substance is actually in this fully deprotonated form. So we need to establish some sort of math that would explain how much of it is available. I mean, obviously you can look at this picture and say y4 minus is highest when pH is greater than pK6. pK6 being, what was it, 10.35? 10.37. So that means if your pH value is, I don't know, anywhere above 9 or 10, that's where we're really going to start to see the emergence of this y4 minus form. But we want some math to back that up. And yes, I know that pH equals pK6 is a helpful number, but we're going to need more numbers than that. Was I holding down a button? There we go. So as you remember, the fractional composition is referred to by the symbol alpha, and that it can be used not just to talk about the fraction of deprotonation or fraction of association or dissociation. We can use it to refer to several species. So we can say alpha y4 minus, we can say alpha h6y2 plus. We can put in each of those forms of EDTA. But because we are more concerned about the y4 minus form, this is bad, I should fix this, y4 minus. I meant to fix all the formulas, it looks like I missed one. I want to come up with 2 equations to determine that. One is a function of pH and the other isn't. We're going to talk about this last point after I put up the formulas, but hit the pause button. I think you know how to do this because we've talked about diprotic and triprotic systems. It's a lot to write, I know. Try and actually figure it out. I'm putting down my pencil for a little bit. It's a good water break for me. Take 15, 30 seconds or hit the pause button if you need to. It is a new show. Excellent. So hopefully the 2 equations you came up with are this. I'm going to erase my handwriting to get it out of the way. As we saw, so in a purely mass balance form, the fraction that is in the form of y4 minus would be equal to the concentration of y4 minus at equilibrium divided by this whole big fraction, which we're going to call, like, basically it's our mass balance. We're going to, for the purposes of chapter 11, use this term EDTA in brackets to refer to all EDTA species that are not currently bound to a metal. So this is all of the acid-base EDTA species without having them actually chelating or complexing or acting as a ligand to anything. So if you had a solution of EDTA by itself, no metals in it, that would be what that refers to. So that number is highly variable depending on the situation, but we are going to start using that number because otherwise, to actually do math moving forward, we would have to calculate all 7 of those concentrations to be able to use them. Additionally, we also know that that equation works, obviously, because it's a mass balance and the fraction that's in that form is part over whole. I get that. But we also know that we were able to, for these monoproduct systems, we were able to figure out like the fraction in A minus is equal to Ka over H plus times, or plus Ka. If it's a diproduct system, we knew that the fully deprotonated form is equal to K1, K2 over H plus squared plus H plus times K1 plus K1, K2. If it was a triproduct system, the fully deprotonated A3 minus would be equal to K1, K2, K3 over H plus cubed plus H plus squared, K1 plus H plus K1, K2 plus K1, K2, K3, and there's this pattern that starts emerging. So instead of using, because to solve for all of those Y species, you have to know all the K's anyway. You can use H plus and K values to write the fraction in the fully deprotonated form is equal to the product of all of the K values divided by this denominator term, shown by the capital letter D, which is H plus to the sixth plus H plus to the fifth times K1 plus H plus to the fourth times K1, K2, and so on and so forth. And it's this really big denominator and it takes a really long time to calculate, so I'm going to make you do it once for this lesson and then we're going to move on from it. But I just want to put it out there, both of these could be used. Arguably, I think this formula is the more useful formula because it involves less solving before you calculate it. But I'm going to give you some practice. I can answer this one. Alpha y4 minus is the fraction of total EDTA that is, oh wow, fully deprotonated. Okay. I'm going to give you, you know what? I'm going to give you time to solve this, but in that time, I'm going to write out the work. If you want to hit the pause button and you work it out yourself, or grab your calculator or your spreadsheet, because that's kind of what I did, you can do that, but I'm actually going to try and plug in what to do here. But to calculate alpha y4 minus at a pH of 3.50, that would be equal to, and this is probably going to take me a solid chunk of time to write. I'm going to write the denominator first. Like I said, I'm only going to make you do it once, and so if I'm going to make you do it once, I should do it once. I don't know if this is going to fit. I don't think it's going to fit. I need a second line. I need a third line. I need a third line. Times 10 to the negative 6.13 times 10 to the negative 10.37. And all of that, the denominator is basically going to be what I just wrote at the end, 10 to the 0 times 10 to the negative 1.5 times 10 to the negative 2 times 10 to the negative 2.69 times 10 to the negative 6.13 times 10 to the negative 10.37. And if you do all of that and you use your calculator correctly and you get all your parentheses right, my hand hurts, you should get 2.72 times 10 to the negative 10th. No units there because this is a fraction. I mean, basically it's a percentage that you haven't multiplied yet, but that's such a small percentage. That's like parts per billion territory. All that tells me is that at a pH of 3.5, the amount of EDTA that is in the fully deprotonated form is very low, which should be consistent with the graph that we saw. Where'd the graph go? There. If this highlighted line is the Y4 minus composition fraction, we're talking about a pH of 3.5, which is, yeah, like if we were to trace this line down, it's going to be pretty close to 0, and that all makes sense. Compare the values of that at the pH of 3.5 to the values of H2Y2 minus and H4Y. So H2Y2 minus is here, and the H4Y is there. And so if we're at a pH of 3.5, well, given that 3.5 is closest to 2.6, I'm going to say that this is largest. And I'm just going to hazard a guess to say that this is smallest because it's the furthest away. No, that's wrong. Not that one. This one. No, I had it right in the first place. It's hard because K4 doesn't refer to 4 H's. It refers to 2 H's because you lose them, right? You lose them in the opposite order that they're numbered. So I had it right the first time. As pH goes up, the fraction of the deprotonated amount goes up, and the fraction of the fully protonated goes down. And then what you see in the middle is that everything's going up and going down in soup, but also, you know, you could take the average values of all these to figure out the pH where these are all at maxima, right? So in between K1 and K2 is H5Y plus, and its maximum should be at about 0.75, which we see is about true. And then between 1.5 and 2, you know, that should be 1.75. And we should see a maximum for H4Y at about 1.75, which we do. So the math is still there for the whole like pH of the intermediate being an average of the next door K values. But what I'm asking is to take that into a little bit further to say, like, what does this solution look like at a certain pH? So at a pH of 3.5, not only is H2Y2 minus the predominant species and the largest in terms of fraction, but you can also say that there's more H4Y than there is Y4 minus, and you can keep pushing past that. So to summarize everything we've talked about today, H6Y 2 plus all the way down to Y4 minus all get lumped together to be called EDTA. Fractions in each form are a function of pH, and you know, the most important one that we're going to use, I keep doing that. Y's and 4's for some reason, man. Y's and 4's. Okay. I'm not going to write it out. Don't worry. I told you I'd make you do it once. And that's the most important one. Now, it's so important chemically, and it's so useful mathematically that in your textbook, the first table that you're going to see is shown above my head, table 11-1, we're going to just assume everything's at 25 Celsius and a mu of 0.1. But there you go. So we had our graph for y4 minus, but in addition to this graph showing this line for y4 minus, you also get this reference table that shows you the actual numerical values at whole number pHs. This means that if you didn't have a whole number pH, you'd have to calculate it, but also it means moving forward for the ease of calculation, I'm going to give you whole number pH values, and I guess that means we should buffer it. So all of this acid-base behavior of EDTA is present and should be thought of, but it's not going to directly impact the chemistry happening with the metal ions that it's binding to, because we're going to fix the pH. So it's like this whole time running in the back of our mind is, yeah, EDTA does this acid-base stuff. We're not going to worry about it because we fixed the pH, which is funny because the rest of the year is about having an unfixed pH and figuring out what it is. But hopefully this sets up the platform to talk about how EDTA interacts with metal ions at a fixed pH and removes this as a variable. Thanks for watching.